Hello everybody, welcome into another lesson. So today is going to be limits at infinity part 2. This is where we're going to take limits at infinity of other types of functions. To start with, we're going to deal with some exponential functions. So we're given here first the limit as x approaches infinity of e to the negative x. And on the screen beside me, you'll see the graph of e to the negative x. Well, if we look at it from a graphical standpoint, if I keep putting in higher and higher values of x, notice I keep getting closer and closer to a y value of 0. I'm going to get infinitely close to 0. And actually that's the limit, because if we take e to the negative x, well, that's the same thing as 1 over e to the x because of the properties of negative exponents. So we can write that as the limit as x approaches infinity of 1 over e to the positive x because of the properties of negative exponents, which if you put in higher and higher values of x, you're going to go to infinity in the denominator. And 1 divided by higher and higher numbers is going to bring you infinitely closer to 0. So in fact, the limit as x approaches infinity of e to the negative x would be 0. And that would be the same for 5 to the negative x, 2 to the negative x, 10 to the negative x, what have you. If you have x to the limit as x approaches infinity of any exponential function to a negative variable power, that limit is going to be 0. Now, let's also look at the limit as x approaches negative infinity of 5 to the positive x. So let's change this. We're going to take 5 to the positive x. Let's graph that. So now on your screen you see y equals 5 to the x being graphed. And graphically, if we keep going further and further left, x approaches negative infinity, you would end up getting a limit of 0. Well, you put in 5 to some negative number, that becomes the same as 1 over 5 to the positive x. And then you just have those values that get infinitely bigger and bigger. Your limit is also going to go to 0. So in general, if you have a negative exponential function and you take the limit as x approaches positive infinity, it's going to go to 0. If you have a positive exponential function and you take the limit as x approaches negative infinity, it's also going to go to 0. Now, of course, I think it's pretty obvious here that, let's say I took the limit as x approaches infinity of e to the positive x, well, that would just be e to the infinity, which would just give you infinity. That one should be pretty obvious. And then let's say I took the limit as x approaches negative infinity of 5 to the negative x. Well, a negative on a negative is a positive. That would actually make your limit approach infinity. So those really aren't so bad. Those are fairly obvious. Now, what if we had some inverse trig functions? For example, let's say I take the limit as x approaches infinity of the inverse tangent of x. And we'll also do the limit as x approaches negative infinity of the inverse tangent of x. Why don't we do those? And I'll even put them on the screen here for you. I'll put the inverse tangent of x on the screen so you could see it. Let's zoom out some so you can actually see it. I'm trying to, there we go, that's what I needed. I was just having a hard time doing the zooming. This can be a bit wonky, but there's a good zoom of the inverse tangent function. Alright, so graphically, as x approaches infinity of the inverse tangent of x, you see a horizontal asymptote. And same as x approaches negative infinity for that function. But what is the domain of the inverse tangent function, of course, is the set of all real numbers. But what's the range of the inverse tangent function? It goes from negative pi over 2 to pi over 2, right? So as I put in higher and higher values of x, as x approaches infinity of the inverse tangent function of x, we're going to reach pi over 2. I would actually end up getting a limit of pi over 2 for x approaches infinity. Now, if you also look at that same graph, as x approaches negative infinity of the inverse tangent of x, since we know the range goes to negative pi over 2 at the lowest end, the limit as x approaches negative infinity of this function would be negative pi over 2. So those are some limits at infinity for the inverse tangent function. Now, let's go back here because I really have no way to graph it. Let's change this a little bit. What if I took the limit as x approaches infinity of the inverse cotangent of x and the limit as x approaches negative infinity of the inverse cotangent of x? Well, again, the domain of the inverse cotangent function is all real numbers, but what about the range? Well, your range of the inverse cotangent function is from 0 to pi. So if I put in as x approaches infinity, I'm actually the limit as x approaches infinity of the inverse cotangent function's going to take me to 0. And then, as x approaches negative infinity of the inverse cotangent of x, that's going to take me to pi. So my limit as x approaches negative infinity of the inverse cotangent of x would end up being pi, if we think about the graph of the if we think about the cotangent function graph and then the inverse cotangent function graph. So those are some basic inverse trig function limits. Now, let me throw a curveball at you a bit here. What if we did the limit as x approaches infinity of the inverse tangent function of x squared minus x to the fourth? This kind of ties in with the polynomial functions we did yesterday. If we look at that x squared minus x to the fourth part, what is this? Well, we notice that, of course, x to the fourth is going to increase much faster than x squared. So this would really be the tangent, the inverse tangent of negative infinity, which as you go towards negative infinity for the inverse tangent, you would just end up getting negative pi over 2. So in this case, the limit would be negative pi over 2 because x to the fourth increases faster than x squared, so you'll end up with a negative infinity inside of the inverse tangent, which would take you towards negative pi over 2. So knowing how these work are very good to know how these inverse trig functions work. Now, let's do this. The limit as x approaches infinity of the sine of x, the limit as x approaches negative infinity of the sine of x, the limit as x approaches infinity of the cosine of x, and the limit as x approaches negative infinity of the cosine of x. So we're going to do some basic trig functions, just the sine and cosine functions. So we're taking the limit as x approaches infinity of the sine of x. Well, now it's true that for both the sine and cosine functions, the domain is the set of all real numbers. There's no number you could put in x that it can't be. It's defined for all real numbers. But what's the range? The range is for both sine and cosine is from -1 inclusive to 1 inclusive. Now, if we look at the graphs of both sine and cosine, what's true? The graph continues to oscillate infinitely between y values of -1 and 1. And it does that infinitely. It doesn't stop. What that means is it's going to do that infinitely, so we can't come up with a precise value of the limit as x approaches infinity. So infinite limits at infinity and negative infinity for both sine and cosine of x do not exist, because it never settles down to a finite value. So knowing your graphs of these trig functions is very useful for helping you know limits at infinity and negative infinity of sine and cosine, because your y values continue to oscillate between -1 and 1 infinitely, and it never settles down to a specific value. So those are some basic trig functions. Now let's change it on you a bit here. Let's say I have you do the limit as x approaches infinity of the sine of x over x. In fact, I'll throw that up on the screen. This is going to be a bit different. First, you're probably looking at the numerator and thinking, well, you would think that alone would make this limit not exist, but we're actually going to see that it does exist. So what if I took the sine of x and then I divide that by x? Let's graph. Actually, let's zoom in. So if you look here, I'm putting in infinitely larger and larger values since we're approaching infinity of the sine of x over x. You see a spike right at 0. And actually in the next lesson we're going to deal with some of these limits as they approach 0. That's a whole separate lesson. There's a trick for these without even having to use graphs. But if you put in higher and higher values of x, you actually approach 0 for sine of x over x. The reason being is, yes, it's true that the sine of x itself oscillates between -1 and 1, But if you look at your denominator, the higher and higher values you put in, it's going to make that oscillation basically insignificant to where you're going to get infinitely close to zero. So the limit as x approaches infinity of sine of x divided by x would actually be 0. Now, what if we do the same for negative infinity? The limit as x approaches negative infinity of the sine of x divided by x. Well, if it helps you, let's look at the left branch of the graph. So there's the left branch of the graph as we approach negative infinity. Again, as true in the numerator, you'll oscillate infinitely between -1 and 1. But if you put in infinitely large negative values in your denominator, it's going to make that oscillation basically insignificant, and you're going to get infinitely close to a y value of 0. So the limit as x approaches infinity of the sine of x over x is 0, and it's also true as x approaches negative infinity. You'll get 0. Alright, now of course we need to talk about the cosine of x divided by x. The graph's a bit different. So let's deal with the limit as x approaches infinity of the cosine of x divided by x. And I'll throw that graph up on the screen here. Now, as you see, it looks like we have an infinite discontinuity right around 0. But that's still irrelevant. Right around x equals 0, we have an infinite discontinuity. But that doesn't matter. We'll actually deal with the limit as x approaches 0 of this function in the next lesson. But right now, we're only interested in the limit as x approaches infinity and negative infinity. First, let's deal with infinity. Once again, you see the higher the values you put in for x, yes, it's true, in the numerator, it's still going to oscillate between -1 and 1 for your y. But if you put in infinitely bigger values in the denominator, you're going to get close to 0. So the limit as x approaches infinity of the cosine of x divided by x as x approaches infinity is going to be 0. And now let's deal with the left branch. And you guessed it, the same holds true as x approaches negative infinity. The limit is going to go to 0. The sine of x divided by x and cosine of x divided by x are actually very surprisingly common functions. Those are very, very common functions. Now, of course, we got one more trig function I'd like to deal with, and that's going to be the tangent of x divided by x. What a mess. What a hot mess. You're all over the place. You got some big spikes. But as you can see, due to those spikes all over the place, you never really settle down on finite values. So you could almost say that the limit as x approaches infinity and negative infinity of the tangent of x all over x, due to what we're seeing graphically, these do not exist, because you have, it would look like it settles towards 0, but you have all those spikes in between with various different values. So these limits actually wouldn't exist for that reason. Alright, now there is one more I'd like to talk about. Let's get into a logarithmic rational function. Let's get into the limit. Whoops, I already wrote the limit. The limit as x approaches infinity, if I could write today, of the natural log of x divided by x. Now, I can definitely explain this algebraically in a second, but it might help for you to graphically see this. Let's say I take, where's my natural log at? Here it is. Natural log of x divided by x. Let's graph that. I'm trying to give you a good graphic of this. There, I think I gave you a pretty good graph of the natural log of x divided by x. The limit as x approaches infinity of the natural log of x divided by x. So if you look at your graph, graphically we can see, again, you're approaching a y value of 0. But why is that? What's the algebra behind it? Well, if you notice the general graph of your logarithmic function, generally speaking, the natural log of x, or any logarithmic function of x, is increasing at a slower rate than x itself. For example, if you take the natural log of 2, that value is less than 2 itself. If you take the natural log of 8, that's less than 8 itself. The natural log of 100, it's less than 100 itself. So the moral of the story is you can basically treat this like you would a rational function where the degree of the numerator is less than that of the denominator, which would mean that this limit would actually go to 0 for that reason. And when we get into L'Hospital's rule, it'll become more obvious. That'll give us a trick to where we can solve this limit without even needing the graph or having to look at it. But I just wanted to show this to you in a graphical sense so you could see where this is coming from. So those are really all of the special types. This is a non-exhaustive list. We could definitely have more than this, but these are some of the most common ones you'll see in calculus. So the next lesson we're going to focus on trig function limits, rational trig function limits I should say. We will do some of those, and we'll learn some methods for evaluating those. We will focus primarily on when the limit approaches 0 of those special trig functions. So I hope everybody has a great day. Take care.